Here's a really cool integral that looks very simple, but is actually very involved. But it's a lot of fun. So let's solve it. Now, yeah, you should know how to get started because we're gonna use the residue theorem. So even though this is not given on a closed contour, we're gonna make it about a closed contour. Um, and there are very few details I'm going to leave out, and in case you need to fill in those details, I've linked a video below this that'll have those details. Yeah, all right, cool, let's get started. So as I said, we're going to be about a closed contour, so the residue theorem can be applied, and let's say that our closed contour is C. Then the residue theorem says that the value of f of z dz on that closed contour is equal to 2 pi I times the sum of the residues aj, where aj, right, is the residue of f at the singularity zj. So you see we're gonna need to find the singularities of our function. Now here our function f, f of z is going to be 1 over z cubed plus a cubed. Let me write that a little bit higher, y'all. So 1 over z cubed plus a cubed. Yeah? Okay. Now, the singularities from here are going to be 3. One of them is going to be at a 60-degree angle, and another is going to be at a 180-degree angle, and another at 300-degree angle. So they're going to be 120 degrees apart, the 3 singularities of this guy, yeah? But we're going to use the closed contour C that is in here, right? Our contour is what I'm shading right now, and it's 120 degrees, and so it's it's a part of, it's a quarter circle in the first quadrant, and a little bit more than that, so 30 degrees more in the second quadrant, right? Okay, beyond the vertical of the first quadrant. Okay, all right, cool. So, well, I didn't need to describe that. You can see the contour. I've shaded it. All right, and that's all to say that we basically don't need the 2 singularities that are outside of that contour. So we're really only interested in the singularity inside of our contour, and let's call it Z1, the singularity. So we're only interested in finding A1, the residue that corresponds to Z1. Now we have many ways to find residues, but one efficient way, when we have a rational function where the degree of the denominator is 2 or more than the degree of the numerator, is to take the numerator and evaluate it at z1, and then take the denominator's derivative and evaluate it also at z1. So basically, if your function f is n of z over d of z, I'm saying that you should do, to find the residue aj, you should do n of zj divided by d prime of zj. Now, n in our case is 1, so we leave it alone. There's nothing to plug into that. But d prime is going to be 3z squared, right? The derivative of that. And in it, we're going to plug in a1, so we're going to get 3z1 squared. Cool. So this is our residue, yeah? And the only residue we have, and the only residue we care about. All right, nice. So then now we say that A1 is going to equal, well, we need to figure out what this Z1 is. Well, since it's it comes from the zeros of this guy, and so it's where Z cubed plus A cubed equals 0. We said that there are 3 of them, and we only care about this first one. This first one is going to be Z1 equals a e to the I times pi over 3. You can do that more carefully if you'd like. So we see that Z1 here is a e to the I pi over 3 right there. Yeah? Okay, cool. So A1 is going to be 1 over 3 times Z1 squared. So that's a e to the I pi over 3 all squared, right? Okay, cool. So then we go, this goes away, and we've got that A1 is equal to 1 over 3a squared, and then it's e to the 2 pi I over 3. Yeah? Now, recall we have to multiply the sum of the residues by 2 pi I to find the value of the integral. So we need to multiply this by 2 pi I, basically. Easy. Right? We just replace the numerator with 2 pi I, and that's what we need. So this is 2 pi I, And now we have found the value of the integral over the closed contour, right? Okay, so here it is. This here, right? This here is the value of the integral of that function over this contour, right? And yeah, so that's that. Now let's talk about how our contour is made up and how this has everything to do with the integral we're after, right? Okay, now first notice that our contour is composed of three things. One is the line segment from the origin, let's say having radius r, right? So let's say that the radius is r. So the line segment from the origin with radius capital R going this way to R, right? So let's say that this portion of our contour is CX, and then we have this arc going from here to here. Well, I missed tracing it well, but you get it. So you have that arc, and let's say that that's CR, right? And then once you get here, which is radially out an R amount, we'd like you to return back to the origin. So follow CR this way, and then back to the origin this way. And this here is at 120 degree from the positive x-axis, right? This line here. And it's intentionally chosen. It simplifies a lot of the work that's to come. So yeah, we could have returned over some line segment over here, and we would have still enclosed our singularity and so on. But we intentionally chose to return this way because it simplifies things, and you'll see. All right. So now we're going to say that the integral over the closed contour is the same as the integral over cx plus cx of f, right? And it's f of z dz, but I'll just write f. And then plus the integral over cr of f, and then plus the integral over, and let's say this last return coming back along that line is CL. Yeah? Okay, now by the same details, or by following the details of the video I link below this one, you can show very easily that the integral over CR of f is going to go to 0. The details of that proof are in the video I link below this, so check that out. So what we're saying is the value of the integral over the closed contour is just the sum of the integral over cx and cl. Yeah? Okay, so now let's talk about the integral over cx. Well, the integral over cx of f, right, is equal to the integral from 0 to r, right, from 0 to r of dx over x cubed plus a cubed, right? So basically the integral over cx, right, over that portion is just the same as the integral that we're trying to find when r goes to infinity. And invariably we're going to send r to infinity. I don't know if I said that, but the integral over cr, which we'd written here, of f, goes to 0 when r goes to infinity. Because ultimately, eventually, we're going to say r goes to infinity, right? And that's how we're going to have this looking like the actual integral we're after. Sorry if I missed that detail and I'm doing it out of order now. Anyway, we already said the integral over CR goes to 0 as r goes to infinity, so I could delete that part and we're on to CX. So now, as I just said, r is going to eventually go to infinity, so this here is equal to the integral we're after, right? And let's call the integral we're after I. So if this is I, then the integral over cx is I. Okay, cool. So right now that means that we've got this. We've got that this is equal to I plus, and then now we just need to figure out what that is, right? Okay, now the integral over CL, we can approach the following way, which is, let's say the z in polar coordinates is r e to the I theta. Well, notice that when we're on CL, we're on a specific theta, namely 120 degrees. that's 2 pi over 3. So theta is 2 pi over 3. And then that'd mean that dz is equal to e to the 2 pi I over 3 dr, right? From there, right? dz equals this, right? Okay, cool. And furthermore, that z cubed, right, for this part is going to equal r e to the I 2 pi over 3 cubed. That's r cubed, and then e to the 3 times 2 pi I over 3. This 3 and this 3 take care of each other, so we have r cubed e to the 2 pi I, but e to the 2 pi I is 1, so we just have r cubed. That is z cubed is equal to r cubed. Nice. So that means that since z cubed is equal to r cubed, that means that the integral over CL could be done the following way. The integral over CL of f of z dz is equal to, well, first, notice that we're going from r to 0, right, over CL, if we follow the correct orientation. So it's going to be from r to 0 of what? Of dx is equivalent to dz, so that's e to the 2 pi I over 3 dr, that's dx, and then over, and then we have, that's z cubed, but that's r cubed, and then plus a cubed. But wait, now if we change the order of integration to go from 0 to r, we just need to put a negative in front of the integral. So we put 0 here, and then r here, and then a negative right here. So now we've got negative, and then this is just a constant, so we can take out that constant. So it's negative e to the 2 pi I divided by 3 times the integral from 0 to r of dr over r cubed plus a cubed. But wait, as I've already said, we're going to send r to infinity. So when we send r to infinity, this integral here is I, the integral we're after. So the integral over CL is really just this times I. So, because r is going to go to infinity, right? So we've got the integral over CL is negative e to the 2 pi I over 3 times capital I, the original integral we're trying to find. All right, cool. So we've got now, in summary, that CX plus CL integrals of f, which equal the integral over the closed contour, which in turn equals this, are going to equal I, which is what CX equals, right? Or the integral over CX equals I plus, we just found the integral over CL, which is actually not plus, minus. So so let's put a minus right here. But yeah, we need to be in black. Also minus, and then it's e to the 2 pi I over 3 times I. So we have that this equals this, and that's how we're going to solve for I and what remains of this video. Yeah, I hope you've found the rest of it so far as joyful as I have. Minus like some like ambulance sirens I've heard in the background that you may not have heard, which is so annoying. I think they're sent like to annoy me and to ruin my videos. I've had to re-record this particular video a few times because ambulance sirens ruined it, but other reasons too, so I'm not gonna just blame them. But I swear they're not saving lives, they're just like sent to like destroy my videos. Okay, I think that like everything in the universe is about you and at the same time not about you, but in the view that it is about you, the ambulances are in fact sent to destroy my videos. Okay, anyway, this here, right, equals, by the sequence of arguments that we've followed up to this point, it equals that. So that's 2 pi I divided by 3a squared e to the 2 pi I over 3, but I could just write that upstairs as e to the negative 2 pi I over 3. And now, clearly, to solve for I, what I need to do is divide by this on both sides, right? Okay, so let's copy and paste it. Why not? Save a little bit of effort. So let's put that right there. And then, can we cut it from here? That would be nice. And then slide the I. See, just that costed me, like, now I can't copy and paste anymore, or cut even. So anyway, this is gone, right? We've divided by it on both sides. So this equals I. But wait, what we're going to do here, and this is like the whole thing being multiplied, right? What we're going to do here, which is pretty clever, is multiply both the numerator and the denominator of this expression by e to the, I'll do it in blue. We're going to multiply numerator and denominator by e to the negative pi over 3 times I. So numerator and denominator by e to the negative pi over 3 times I. When we do, notice that this and this are going to multiply to e to the negative I pi, which equals, in turn, negative 1. So basically I'm saying you could get rid of this, you could get rid of this, and write negative 1 in place of them. So from all that, we just have a negative 1. So I equals negative 1, and let me, I guess, start writing in red. So I, the integral we're after, equals negative 1. But wait, there's stuff we have forgotten, namely 2 pi I. So instead of negative 1, I'm going to write negative pi. And intentionally group the 2i. And write it in a different color, right? I haven't left anything out, right? Notice, as I already said, these two combine to negative 1. And then I have negative 1 times pi is negative pi, right there. And then I have 2i, the only things remaining from the numerator. And then in the denominator, now we have this distributed to this and that is going to say, first, the 1 turns into e to the negative pi over 3 times I, and then the and I'm gonna write this in blue actually once I distribute that, right? And otherwise my color coding won't make sense. E to the negative pi over 3 times I, and then when I distribute this to that, it's gonna say well, first I have the minus sign, but after the minus sign it's gonna say e to the positive pi over 3 times I. And of course I have the 3a squared as well, and I'm gonna write that in red. So 3a squared. Now we're gonna do this. We're gonna take this negative and cancel it and write a plus there and a minus in front of this, right? So that's equivalent to multiplying the numerator and the denominator by a negative 1. And if I do that, let's see if I can erase. I bet I'm not going to be able to. Yeah, well, it erased some stuff. But basically, now, I could, if I could slide this somewhere and simplify in the space that it occupies. Yes. So from here, let's move over here and simplify. We've got that I, right, which equals this as of now, equals the following, which is pi divided by 3a squared, and then times, and it's 2i divided by, and then it's I could write these guys in reverse order, right? Leading with the positive, which is e to the pi over 3 times I, and then minus e to the negative pi over 3 times I. Well, and it's more that. And observe that since I need space, we're almost done, fellas. Observe that since we have that sine theta, and let me write in a different color. What's that? Blue, I guess. Since sine theta is equal to e to the I theta minus e to the negative I theta over 2I, what we have over here is 1 over sine of pi over 3. So this here, if you watch it carefully, is basically this flipped, so it's 1 over sine, and it's of pi over 3. Yeah? Cool. So that's why we separated the pi and the 2I and all that good stuff, because we anticipated that it was going to work out beautifully like this. So we had this times 1 over sine of pi over 3. But sine of pi over 3 is like root 3 over 2. So 1 over sine of pi over 3 is 2 over root 3. So we've got that this is pi over 3a squared times 2 over root 3. Which means, finalement, that our integral has the following value, which is that I equals, this equals 2 pi divided by 3a squared root 3. Yeah? Alright, I hope you enjoyed this as much as I enjoyed it. Alright, take care. Keep watching.